All right, we'll start the slideshow. We'll try to start the slideshow from the current slide and then go to the next slide. Okay. Let me make these last few announcements. They all mostly have to do with my office hours, and they are wrecked for the rest of the week almost. Starting today, they have this health screening for Public Education Employees Wellness Program. They don't require us to do it, but they say if we don't do it, our premiums go up. So this gives us a thing. So the only time they have it is today on this campus, is today from 9 to 1. Well, I'm in class at 9. I'm in class at 9:30. I'm in class until 11:10. And then, so I'm only free from 11:15 until 12 when I have the other class starting, okay, your class, okay? So I've got to do it sometime between 11:15 and 12, which is when I usually eat. Doesn't look like I'll be eating today, but anyway, so I have to be there. That's normally my office hours. Not going to be in the office much during that time. Now, if that screening goes real quickly, then I'll be back in the office for a little while. So I've got class starting at 12. Then, most of my office hours on Mondays and Wednesdays are 3:15 to 5:15. Not today. I've got to run several pieces of documentation over to the Birmingham campus today, and so I'm going to have to leave shortly after my Marcus is here. Shortly after when my 3:15 class ends, I'm going to have to leave pretty soon after that to go to Birmingham. So I will have office hours, but they won't be here. They'll be on Birmingham campus. So today's office hours pretty much shot everywhere. Okay. Then tomorrow, and I checked this morning, that's one of the things I tried to do in the time I got here early, there is a chance I'll be taking my physical science class on a field trip, but since they didn't respond to me yesterday, I'm guessing it won't be tomorrow. They could still respond today. I'll find out. But if that's the case, then my office hours tomorrow will probably be somewhat curtailed because I might have to anyway, whether I go on the field trip or not, go over and pick up the information on the vehicle that I'm going to be driving on Friday. Okay, which leads to the next part of my thing. Because normally on Tuesdays and Thursdays I have office hours from 10:45 until 12:30. If I have to pick up the vehicle, or at least the documentation for the vehicle, then I'm going to have to leave right at 10:45, get over there, get there maybe by 11:15, get back here by 11:45, and then teach class. But yeah, it's going to be really tight. So tomorrow's office hours, pretty good possibility they'll be curtailed as well. Then, okay, if that's not enough, on Friday, last Friday I had treatment, so I was at the clinic by 6:30 and didn't leave until 4:30, so I wasn't on campus at all last Friday. This Friday, we're going to Opelika. The math, about 7 math instructors are going down for our annual meetings there. So we will be gone all day then, leaving around 6 in the morning and getting back around 6 in the evening. So I'll be on campus, but not very long, and there'll be times you're probably not on campus. So Friday's office hours are shot. Next Friday, also, I have my annual physical, 8 o'clock in the morning, so I won't be coming in at 7:45. I'll be at the Clucking Clinic at 7:45, and then I'll be coming here after that's over. So that's probably going to be 9:45 or 10, somewhere around there. But that's on the Birmingham campus. So I will be on campus, knock on wood, but I just don't know when. Tons of announcements today. Sorry about that. All right. Any questions on anything we've covered so far? Okay. We are on page 62. We just got started with 2.3. And here we're talking about the inverse of a matrix. So I think we got right down to the definition. And I noticed that, well, all three of you have books, right? But I'm not sure about Jonathan. He's the other student. What is it? Yeah, Jonathan. Boy, I didn't realize it. Just noticed it. This class is all last part of the alphabet. Jonathan's at the top of the alphabet, Rice is at the beginning, and we go through two Williams. So no A's, B, C, D, E, F, G, nothing until we get to R's. Wow. Okay, that's beside the point. All right, definition of an inverse matrix. Now, for a matrix to have an inverse, tell me some characteristics of that matrix. What must the matrix be if it's going to have an inverse? Square, okay? So let's let an n by n matrix, A, only one that could, is invertible, okay? Also, didn't I write this last time? I did. Why do I have my mark there? Okay? So I already went over this, right? Second? We didn't. Okay. So I must have just put the mark in the wrong places. Okay. What's that? 62, right? I got marked to 62. I think we did that. We introduced the first part, and I think we went over the matrix, the definition of the inverse. Okay? Okay, we did that, but I think that was a while back. Yeah, we did, and I think we did. Okay, didn't we do example 9 last time on page 58? We did do that, didn't we? What's that? Right. Okay, we did discovery. What? Okay, we already did example 9, right? Okay, and we did example 10 on page, yeah, okay. So I think we got into 2.3, just barely got there, and the question is, did I do this definition? And you think I did? I thought so too, because it all seems familiar, but I've done it several times. So, picking up then after the definition, non-square matrices cannot have inverses, okay? Cannot, okay? So don't ever try to find the inverse of a non-square matrix. I'll call it a rectangular matrix. To see this, note that if A has size m by n, and B is of size n by m, where m is not equal to n, then the products AB and BA are different sizes, can't be equal to each other, obviously, okay? Not all square matrices have inverse. Just because it's square, it has to be square before it can possibly have an inverse, but not all square matrices do have inverses, okay? And example 4 is coming up, we'll see that. So this next theorem, 2.7, okay, we've got it almost started here. If A is an invertible matrix, okay, then its inverse is unique, okay? If A is invertible, then the inverse is unique. What that means, if A has an inverse, it has one and only one inverse. You can't have one matrix that has two different inverses. Can't happen. It's one and only one. It's unique. The inverse of A is denoted by A inverse. Okay? I think we have mentioned this before, or maybe not. That minus 1, superscript minus 1, does not mean 1 over A. Okay? It does for variables, it does for real numbers, it doesn't for matrices, just like it doesn't for functions. Just like f to the minus 1 is the inverse function of function f, a to the minus 1 is the inverse matrix for matrix A. Okay. Now, they do a little proof here, and it's pretty straightforward, and since, well, actually my one math major isn't here, but in case he may listen, so let's do it. We've already been told that A was an invertible matrix. That was the given. Because that's true, we know there's at least one matrix B such that AB, what has to be true? If A is an invertible matrix and B is its inverse, what's the product of A times B? Okay, it's also B times A. You're absolutely right. This is the one and almost only situation you'll find that true, that the multiplication is commutative. But what is that product, AB or BA? Say again? No, the B is the inverse of A. But this result of that product is the identity matrix of that same size n, whatever size that was. Remember, A has to be square, B has to be square. They have to be the same size. That would be I. Okay. Now, this is trying to show that that inverse is unique. Let's suppose it's not unique, that there's some other matrix, C, not equal to B, C cannot equal B, some other matrix, so that AC is also CA and is also IN. Let's just imagine that's the case. Okay? Now, if that's not the case, if C is not equal to B, that means B has to be unique. If C is equal. So that's what we're trying to show. Okay? So what we're going to do, start with this statement right here, that AB is equal to the identity matrix. We know that's true. A is invertible, B is the inverse. The product of them is your properly sized identity matrix. Okay? Now, let's imagine the C is there, so let's multiply both sides of the equation by C. Right? That means C times AB is equal to C times I. Right? Okay. Well, what is CA? CA would be the identity matrix, wouldn't it? If this is indeed true, CA is the identity matrix. Identity matrix times B would be CI. But what is C times the identity matrix? That's why we call it identity. What happens if you multiply C times the identity matrix? What happens if you multiply pi fifths times 1? You get pi fifths. Well, here you're multiplying by something equivalent to 1 in matrices. That's C. But IB is what? B. So this shows that B has to equal C. That can't be true. So therefore, there's one and only one identity inverse matrix for B. If indeed, for A, if indeed it has an inverse. Okay? Now, what we usually term then is A inverse. So rather than saying BC or something else, and it's unique, A times A inverse is equal to A inverse times A, and both of those are equal to the identity matrix. So that's the summary here. So let's do example 1, which will illustrate this. Let's suppose that A is a square matrix, minus 1, 2, minus 1, 1. And that B is also a square matrix, 1 minus 2, 1 minus 1. Okay. It says show that B is the inverse of A. What is required for that to be true? The product has to be equal to the identity matrix. So let's do these two together. Can you multiply those two? Sure. What size will you get? 2 by 2. So let's start doing it. Where do you want to start? 1, 1. Okay. Do 1. Row 1 times column 1. What do you get? Second. 1. Negative 1 plus 2 is 1. Next. You want to go across or down? Across? Okay, let's do across. 1, 2. Buckle my shoe. What do you get there? Second? Okay, you get a 2. Okay. 2 minus 2 is 0. Okay, 2, 1. Zero again. Looking good so far. And 2, 2. One. Absolutely. Now, supposedly, BA should also be the identity matrix. So let's just write A over here and do that multiplication that way. -1, 2, -1, 1. Let's multiply this way. Sure enough, we still can do it. Gets a 2 by 2. Let's multiply this way, and what do we get? 1, 0, 0, 1. Yes, we get it. Both ways, you get the identity matrix. Therefore, these have to be inverses of each other. Okay? Make sense? Now, it says find the inverse of a matrix. This is example 2. And they're going to put you through the rigors. Later we'll show you a much easier way. Okay? Here we have matrix A. Is it even possible this has an inverse? What you think? What's required? Has to be square. It is square, so it's a possibility it has an inverse. Okay? It says find the inverse. So they think it has an inverse. Well, that inverse matrix, if it exists, when you multiply it, and we got to give variables and representations, they use x's. I would rather use a's, but they use x's, so I'll use x's. x11, x12, x21, and x22. If it has a matrix, it's going to be another square matrix, same size. And when you multiply them together, what have you got to get? The identity matrix, 1, 0, 0, 1. So let's go through the ringer and see if we can figure that out. Let's do the matrix multiplication. What would that give you? x11 plus 4x21 is equal to 1. Okay? Next, x12 plus 4x22 has to equal 0. Next, okay, equals 0, and 4x12, I'm sorry, minus x12, I'm jumping ahead. Okay. Okay, yeah. Minus x12 minus 3x22 must equal 1. 4 equations for unknowns. Can we solve those? How? Any ideas? Give me a hint. Help me out. How would you go about solving those 4 equations for unknowns? Say again? Do a matrix? Is that what you said? We certainly could. I think in this case, it might be a little easier not to, but we can. Okay? So let's do the matrix. What would the matrix be? One. Okay. Now, I kind of did this on purpose. I'm trying to line those up, these up, and those up. Okay? So let's put a 0 in there. We could do it without, but then I'm afraid I'll get confused. So let's sort of line it up the way it is. That'd be 1, 0, and that is a plus 4 there. 4, 0, 1. You buy that? 1, 0, 4, 0, 1. Right? Second one would be 0, 1, 0, 4, 0. Next. -1. Okay. Yeah, 0. And that is a -3 there. 0, 0. And the last one is 0. Got it? Say that again. Where? Right here. It's 0, -1, 0, right? Yeah, this column is that one. Okay, is that right? Okay. Next. -3, 1. Okay. And then what do we do? Why do we do this anyway? Okay, what do you want to happen? You want that to be 1, got it. What do we want to happen next? 0 is what? Got it here, but not here, so what do we do here? Row 1 plus row 3 is the new row 3. So let's do that. Row 1 plus row 3. Okay? So this becomes, we're using row 1, 1, 0, 4, 0, 1. And we're not using 2 yet, so let's just write it down. 0, 1, 0, 4, 0. Okay? Then add those two, and what do you get? 0, 0, 1, 0, 1. Got it. And the last row, we don't have to do anything, so write it down. 0 minus 1, 0 minus 3, 1. Okay, what do we want to happen next? Okay, go to row 2. We want the first non-zero entry to be a 1. Ding, ding, we got it. And we want zeros above and below it. There's good, there's good. This one, what do we do? Row 2 plus row 4 is the new row 4. Okay? So we're not doing anything to row 1, so write it down. 1, 0, 4, 0, 1. And 0, 1, we're using this one, so write it down. 0, 4, 0. Okay? Row 3 is fine, so write it down. 0, 0, 1, 0, 1. And finally, row 4 is 0, 0, 0. You're getting stuck in the mud, aren't you? 1, 1. All right, got it. All right, we're almost there. In fact, if we want to do Gauss elimination, we could do it right now. Because x22, that's what this column is x22. x22 is equal to 1. x21 is equal to 1. And then we can plug in the others, or we can do Gauss elimination. Just do one more step there. What would that be? What would it be? Okay. Good back. Okay, we wanted a 1 here, 0 below. Got it. We want a 1 here, 0 above and below. Got it. We want a 1 here, 0. Oh, yep, we got that one. Sorry. I think that was a 0. How do we get that to become a 0? Say again? Yeah, say again? Negative row 3, right? Plus row 1. Negative 4, row 3, plus row 1. Okay. And we're changing the first one, so let's go on and change it. What would that be? 1, 0, 0, 0. Say again. One more time. You may have said it, I just can't hear well. Negative 3? Okay, that's what I got too. Everybody got it? Okay. And then I'm going to be really lazy here. I'm going to write in row 3, 0, 0, 1, 0, 1. And write in row 4, 0, 0, 0, 1, 1. But what do we want next to happen to row 2? I cheated. I should have gone and written that, but I'm just being really lazy. Negative row 4 plus row 2. That will wipe that one out. Okay? So negative 4 row 4 plus row 2. And what will that produce? 0. A little louder. 1. All right, good. Next. 0. Next. 0. And next. Second. Really? Negative what? Negative 4. Because you're adding 0 to it. Before you added 1 to it. Yeah, got it? All right, what does this tell you? Remember now, your first column was your x11s. Your second column was x12. Your third column was x21. And your fourth column was x22. Okay? And what does this tell you? x11 is equal to negative 3. x12 is equal to negative 4. x21 is equal to 1. And x22 is equal to 1. So, if we write that as we should, that would be a negative 3, negative 4, 1, 1. I wrote way too big a square there. Okay. That should be the inverse for this one. You want to check it and see if it is? We're multiplying. Don't make me stand up, okay? Negative 3 plus 4 is 1. Good. Yes, that works. Next one. 0. That works. How about the next one? 0. That works. And the last one is 1. Yes, it works. Okay? We found the inverse. We found the inverse of this by doing that. Wasn't that fun? Okay. It was not that hard, but just sort of a little tedious. You know what good mathematicians do? What they are? They're a little lazy. They always try to find an easier way to do it than this. Okay? So good mathematicians have found an easier way. We're going to get to that. Let's see. Sure enough, negative 3, negative 4, 1, 1. That is an inverse. Now, I'll actually show you 2 easier ways. One, generally easier, and the other one, much easier. Okay? But it only works for 2 by 2s, the much easier one. Okay? Now, they go through a generalization here, okay? They take the first and the third one here, this one and that one together, okay? And they do a little matrix with that. And then they do the other little matrix with this one, okay? So they do the x11 plus 4x21 is equal to 1, and minus x11 minus 3x21 is equal to 0. And then off to the side they do another 2 by 2, x12 plus 4x21 is equal to 0, and minus x12 plus 3x22, or minus 3x22 is equal to 1. Because you see, they have nothing in common. You see, everywhere, let's go back to this one. You see, these two, we just eliminated with that. We didn't have to do anything here or here because they were already zeros. These two were already zeros here. We had to clear here. That was already zero, clear here. So we can do those separately, and that's a little bit easier to do, right? So they did those separately like that, okay? Clever, okay? So do those two separately and then solve them simultaneously by joining the identity matrix to the coefficient matrix, okay? Now, what in the world do they mean by that, okay? Well, here's the other thing to note there. When you do this matrix and this matrix, notice the coefficients are the same. 1, 4, negative 1, negative 3. Those are the same. So you're really doing the same thing twice. It's just your solution matrix is different. This one's 1, 0, the other one's 0, 1. Okay? 1, 0, 0, 1. What does that make? The identity matrix. So here's what they're suggesting you do. And this is indeed what you do. Okay? I'm going to erase a fair amount of this, but I do want to leave some things here. Let's erase this. We're going to try to do something a little differently. Rather than solving Gauss-Jordan elimination, all that stuff, which is not that hard to do, it's just sort of tedious. Let's see what we were really doing there. All that work just getting thrown away into ether space here. Okay. Okay. Probably should leave my answer, so I'll leave it. Okay. Now what we just said we were doing was taking this matrix here, which is our original matrix, 1, 4, negative 1, negative 3. Notice that's what we got here. 1, 4, negative 1, negative 3. 1, 4, negative 1, negative 3. Okay? Now what you're going to do is adjoin, okay? Kind of a new word here, adjoin, meaning put what's here. Where you had a 1, 0 from this one, and you had a 0, 1 from this one. Okay? And now let's see what we do. How about doing a Gauss-Jordan? See what we get. Okay? Here we do row 1 plus row 2 is the new row 2. So this becomes, you got a 1, 4, 1, 0. And add those two together, and what do you get? 0. Help me. 1. 1. 1. Very good. And now let's continue Gauss-Jordan elimination. You got a 0 here, a 1 there. So we want to eliminate the 4. What do we do to get that? negative 4, row 2, plus row 1. Let's do that and see what we get. Tell me. 1, 0, negative 3, negative 4. And write down the first one, second one, 0, 1, 1, 1. And guess what we got? What started to be an identity matrix here transformed to be your inverse matrix here. What started to be your matrix A here transformed to be the identity matrix here. So guess what? You just found a much easier way to find the inverse matrix. Adjoin the matrix in question has to be square with the appropriately sized square identity matrix, same size, and then do Gauss-Jordan elimination. And when you get an identity matrix here, you'll get the inverse here. Done. Much easier, right? Far, far easier. Okay. And so what you have here, you start with AI, reduce that, and you wind up with a you wind up with IA inverse. So that's how we wind up getting our inverse matrix. Much easier than doing it term by term by term by term. Ugh, let's not go there. So let's that procedure or algorithm works for any arbitrary n by n matrix. Okay? If A cannot be row reduced to IN, A is not invertible. Okay? It's singular. Okay? This procedure will be formally justified in the next section, I can't wait, after introducing the concept of elementary matrix. Can't wait for that either. Okay. For now, the summary is given as follows, and I guess I'll write that out mostly for Jonathan's sake. If A is a square matrix, okay, order n, so let's just call it n, square matrix. That's the given. What's the procedure? Write the n by 2n adjoint matrix that consists of matrix A adjoined with IN. Okay? That would be n rows, 2 n columns. Because you have n for A and n for I, so that's 2 n columns. Okay? Now, they don't usually put the dotted line in there. I did just to separate them, but they don't. Okay? That's called adjoining the identity matrix to matrix A. Okay? 2. Okay? If possible, row reduce. Okay? If you can't row reduce, guess what? No inverse. If you can row reduce and you produce an identity matrix, when you row reduce this, if that yields some other matrix, and we're going to call it A inverse, I'm going to put that in here. I'm sorry, backwards. If when you do the row reduction, you get I and something else here, that something else is the inverse of A. If you don't get the I, that means you couldn't row reduce, that means there's no inverse. If you can, you got it, you got the inverse. And that's the one and only inverse. Okay. Now, there's a little linear algebra applied at the bottom. It's talking about recalling Hooke's law. Well, there's another potential paper topic. Only try to tie in matrix algebra with Hooke's law. So I just don't want a paper on Hooke's law, but how that pertains to matrix algebra. Okay? But I'll let you continue there, but there's a potential paper topic. Let it go. Let's move on to example 3. I think they're going to ask us to do that, aren't they? Let's see. Find the inverse of this matrix A. What did A better be? Otherwise, you're wasting your time. What did it better be? Square. Is it? Yes. So, does that guarantee it has an inverse? No. But at least it allows you to have an inverse. If it's not square, it can't have an inverse. If it is square, it may have an inverse. So what would we do to find the inverse? Lose that in bracket and put in what? Identity matrix. And how would that go? Say again? A little louder. 1, 0, 0, 0, 1, 0, 0, 0, 1. Now what do we do? Now we do Gauss-Jordan elimination. Okay? What do we want to happen first? 1 in the upper left. Ding, 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 ding. We've already got it. What do we want to happen next? -1 to become a 0. How do we make that happen? Minus Second. Negative row 1 plus row 2. That should do it. Okay? So since we're using row 1, we're just going to write it down. 1 minus 1, 0, 1, 0, 0. Okay? It looks long and arduous. Try doing it with x1, 1, x1, 2, x1, 3. Yeah. You'll go back to this. Okay? So what's our new row 2 now? 0, 1, negative 1, negative 1, 1, 0. Okay, what do we want to happen next? That -6 to become a 0. How do we make that happen? 6, row 1. Yeah, we've already changed row 2. 6 row, you could use row 2, but let's use row 1. 6 row 1 plus row 3 is the new row 3. So what does that give us? 0, negative 4, 3, 6, 0, 1. Got it. What do we want to happen next? First non-zero entry in row 2, we want to be a 1. It already is, so what do we go from there? Okay, a little louder. Okay, you want the -1 to be a 0, -4 to be a 0. How do you get the -1 to be a 0? Row 2 plus row 1. Excellent. Okay, write 1 in there. All right, so this becomes, I'm going to write down row 2 because we're using it. 0, 1, -1, -1, 1, 0. Okay? What's our new row 1? 1, 0, -1, 0, 1, 0. And to get that -4 to become a 0, what do we do? 4 row 2 plus row 3. All right, and what does that give us? 0, 0, -1, okay, 2, 4, 1. Got it. What do we want to happen next? We got the first non-zero entry of row 1 to be a 1, 0 is below it. First non-zero entry of row 2 to be a 1, 0 above and below it. What do we want to happen next? We want the first non-zero entry of row 3 to be a 1. It's not. It's a minus 1. How do we make that a 1? Okay, so I'll write it out. Negative row 3 becomes the new row 3. So that goes plus, minus, minus, minus. See how easy that was? Okay. Now what? You want the zeros to be above that. So how do we make that happen? Row 3 plus row 1. That'll make that one a 0, so let's do that. I'm going to write down row 3. 0, 0, 1, minus 2, minus 4, minus 1. Okay, what's my new row 1? 1, 0, 0, negative 2, negative 3, negative 1. All right. What's next? Row 3 plus row 2 is the new row 2. And what will that be then? 0, 1, 0, negative 3, negative 3, negative 1. That's a really ugly 3 in the middle there, isn't it? Okay. All right. Guess what? We got the A inverse. Right there. Okay. I know y'all want to check it too, don't you? Oh, I can't imagine it. Let's check it by looking in the book. Let's see. They got a negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, negative 1. Yeah, we'll do that and say that if we multiplied the original A by this one, we sure hope we're going to get that. Okay? And you can always check. Okay? I suggest that you check, but like you say, maybe not during class time. Okay? All right. Now, many graphing utilities and software programs can calculate inverses, the inverse of a square matrix. If you use a graphing utility, you may see something similar to the following. For example 3, and I'll let you look at that. If you got a graphing calculator, they will do it. I've done it before on them. Sometimes it's a little bit tedious and a lot of entry, and you have to be very careful when you're doing it. But once you got it done, it's nice. Okay. So you want to move on to example 4. Okay. Yes, let's do example 4. Here's another matrix A. We love our matrix A's, don't we? 1, 2, 0, 3 minus 1, 2, and negative 2, 3, negative 2. Okay. Square matrix, might it have an inverse? Possibility. Does it require to have an inverse? No, it doesn't. How do we determine if it does? You do what? Okay. We adjoin the matrix with what? Identity matrix, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? And then we Gauss Jordan. Okay? What's the first thing we're going to do? Or what do we want to happen first? 1 up there, we got it. Ding! Okay, next. You want the 3 to become a 0. How do you make that happen? Not that hard. Okay, minus. Got the minus part. 3, row 1, plus row 2. Got it. Okay, so since we're using row 1, write it down. 1, 2, 0, 1, 0, 0. Got a lot of writing of numbers down when you deal with matrices, don't you? What's our new row 2? 0, Negative what? 7? Okay. Next. Next. 2. Next. Negative 3. Next. Second. 1. Next. 0. All right. What do we want to happen next? Minus 2 to become a 0. How do we make that happen? You tell me. 2 times row 1 plus row 3. Do it. What do you get? 0. What? 2 times 2 plus 3. 7. All right. Next. A little louder. Is that negative 2? Yeah, negative 2. Okay, next. You say 2? Okay, next. 1. Wait. 0, 1. Okay, I was going to say. All I heard was a 1. I said, no. Okay. Next, what do we want to happen? What we'd love to happen was the first non-zero entry in row 2 to be a 1. And we can make that happen by dividing by negative 7. And that's going to give us a mess. Okay? But let's look ahead a little bit. What would be the next thing we'd want to happen? Zeros below it, right? So why don't we get the zeros below it first, and then we'll come back and make that a 1 if we want to. Because this lines up really nicely to get a 0 there anyway, right? So what does that produce? Let's add row 2 plus row 3 to give us a new row 3. So the row 1 is going to stay the same. 1, 2, 0, 1, 0, 0. Row 2 we'll leave alone for now. 0 minus 7, 2, negative 3, 1, 0. Ugly numbers, but we'll get over it. Okay, and what's our new row 3? 0, 0, 0, 1, 1, 1. Okay. Time out. Do you see anything that's bothersome? What? This, you don't have 0, 0, 1. You're required to have a 0, 0, 1 to get this to be an identity matrix, right? With a row of zeros here, can't happen. Cannot happen. Therefore, inverse doesn't exist. That's a singular matrix. Non-invertible. Can't happen. Now we don't have to worry about putting all those fractions in there. Not going to do any good anyway. Okay? See that? Okay. And you can, if you see something that works out easier before you can do all the fractions, you can do them. Remember those rules, exchanging 2 rows, multiplying 1 row by a non-zero number, or multiplying 1 row by a non-zero number and adding it to another row. Those you can do anytime. You don't have to do them in the same order. So we're not going to add first and then we go back and change. If this had come out as 0, 0, anything other than a 0, well, then I would change that. Okay. But that came out 0, 0, 0. Well, hang it up, Jack. Okay. Good deal. So this one does not have an inverse. It means A is a singular matrix or non-invertible matrix. You cannot find the inverse. Even though it was square, doesn't necessarily have an inverse. Okay. And they did the same thing I did. Now, let's go back. Yeah, we got time? Yeah. We just barely have time. Let's go back And remember I said there was an easy way, easier way, and then a really easy way. Let's go back to this A is equal to, this is example 2 again, a 1, 4, -1, -3. Okay? Now we did it first the long way, and then we showed you the easier way, okay, to get the thing. When it's a 2 by 2, there's even an easier way. And here's how you do it. Let's go back to the page we were just on. We will do a determinant. Do y'all know what a determinant is? We're going to get to it in the next chapter, but do you know what it is now? Any of you? Okay. The determinant of a 2 by 2 matrix is the product of your main diagonal, which would be -3, minus the product of the other diagonal, which would be, and it's a minus, so that would be +4. That's equal to 1, right? That's the determinant of that matrix. Okay. Now, I really want to do, we don't really have time, but I want to show you what the determinant of this 3 by 3 is. And, I guess I won't. We don't have time. So, to get the inverse of this matrix, A, we do 1 over the determinant of A. And actually, I don't like spelling out DET, so I'm going to give you the representation of that. Okay? Let me make sure I use the same thing the book does. Oh, they don't use it here. Yuck. That's the determinant of A, which is 1. So that's just 1. And then what you do next, and this is the trick, a really nice little trick. Exchange the two diagonals. -3, 1. Okay? And negate the off diagonals. -4, 1. Multiply that by 1, and what do you get? This. If you go back to that example 2, what was your inverse matrix? -3, -4, 1, 1. So if you have a 2 by 2 matrix, non-singular, invertible matrix, first find its determinant. Real easy to do. This product minus that product. This happens to be 1. You multiply by 1 over that determinant. 1 over 1 is 1. And then you exchange the two diagonal elements and negate the off diagonal elements. You can't do that with a 3 by 3. Only with a 2 by 2. So I said there was a hard way we did first, then an easier way we did second. This is the easiest way. That's you just almost write it down. You have to determine the determinant, but once you got that done, 1 over that determinant, and then do that little manipulation of the entries, swapping the main diagonal, negating the off diagonals, and multiply that out, and you got it done. Okay, so that was the little blurb at the right before example 5. Now they did it with, I did it with the actual matrix we had done before. They did it this way. Here's matrix A, A, B, C, D, right? Okay? The determinant of A is equal to AD minus BC. Now the only requirement here, if that determinant wound up being 0, that's a singular matrix. It doesn't have an inverse. If it's anything other than 0, okay, then that determinant you put in front 1 over AD minus BC, and then the matrix you write as DA minus B minus C. Swap the two main diagonal elements, negate the off diagonal elements. That's the A inverse.
So you take a
Yes, that means it doesn't have an inverse, but there's no way you can do this kind of stuff with it. And that's what I wanted to do the determinant of that and show you that one is indeed 0. That's why I wanted to, but we didn't have time. So you can go home and do that, okay? Not yet. You're going to be coming to class later, so don't go home yet. But we will pick up next time with example 5, and we'll do 1 or 2, okay? So let me erase this, okay? And let's do some homework exercises. Yes, okay. Do any of the odds 1 through 5. Do any of the odds 7 through 29, a whole passel of those. 27 and 29 are pretty big ones. You might be able to do that or not. I'll let you decide that. And then try to do any of the odds 31 to 35 using the technique I just gave you. And we'll pick up and go from there. Okay? Stop at 35. Any questions? Good deal. We'll see you all later. Various laters, but we'll see you all later. Okay.